Can you guys hear me? Yeah? Yeah? All right, great. All right, this is cool. I can see you too. Somebody make some noise. Can I hear you guys? Okay, cool. Thank you. Okay, this is really cool. I've never done like a remote presentation like this. Okay, this is something I like to do when I have a crowd. Raise your hand if you think human beings are intelligent. Everyone should probably raise their hand. Okay, raise your hand if you think a chimpanzee is intelligent. A chimpanzee. Is a chimpanzee intelligent? Most people think that. Okay, do you think a dog is intelligent? Raise your hand if you would say a dog is intelligent. Okay, what about a mouse? Is a mouse intelligent? Okay, look around a little bit. The hands are going down now. How about a parrot? Is a parrot intelligent? Some yes, some no. Is a chameleon intelligent? A chameleon. Okay, some. Again, less and less. A praying mantis. Does anyone think a praying mantis is intelligent? Fewer. Do you think a bacteria is intelligent? You still. Who thinks that a tree is intelligent? There's always somebody. I see you. Okay, cool. Anyway, that gives you kind of an idea of what the different definitions of intelligence mean to people. I work in the field of intelligence, so that definition is important to me. Okay, well, let me show you some of my slides for a bit, and then I'll probably turn it off and talk some. But I do have some slides. Get to my right screen here. Okay, you guys all see this first slide, the biological path towards strong AI? Yes. Okay, I'm Matt Taylor. I'm the community manager for Numenta. I started there as a software engineer. I've worked at Numenta for 6 years, over 6 years now. All of our code is open source, so I'm sort of the open source community manager. I'm really passionate about this. I read a book by the founder of our company about intelligence a long time ago, and I've just been intrigued ever since, and so I'm really happy to be working here. So here's what I'm going to talk about. I'm going to talk a little about weak AI versus strong AI, and why I don't think weak AI that we're building today is going to turn into strong AI. And then we're going to talk about some brain anatomy. I'm going to talk about pyramidal neurons and some specifics, and then some cortical structures like layers and columns. And I will try to go through the complete HTM theory. It's kind of hard to push through the whole theory in 1 hour, but I'm going to try and do it. And then I'll leave you with some resources at the end and talk about our current research into sensorimotor theory. So I'll kind of leave you with what we're currently working on. So weak AI won't produce intelligence. That's one of the things that I'm positing here. I'm going to turn the screen share off because I'd rather you see my face. Okay, so everything that you guys are doing in AI right now, probably if it's deep learning, if it's ANNs, is I would consider narrow AI or weak AI. And the main thing that makes it that is you can't take one solution that you've created for a target domain and you can't easily move it and apply it to another domain. That's the whole general idea in AGI, or artificial general intelligence. You want to build, if you build something that has general intelligence, you should be able to set it loose in one target area and give it a problem to solve, and take that same thing and give it another problem to solve in another target area, and it should be able to solve it. What we have today is not there, and I don't think we'll get there because of two specific reasons. And now let me share my screen again. So what is missing? There's two big things that are missing. One is neurons and ANNs, the point neuron and basically all artificial neural networks that are underlying deep learning systems are not complex enough. We need a neuron that can represent more states and connect in different ways to each other. That's one major thing. Another major thing we're moving, and this is a harder problem that we're missing, excuse me, is movement. And I'll bet no one in the audience can think of any intelligent thing in the universe that does not move, because I don't think there is anything. We believe, like, at the core of my definition of intelligence, it has to move. In order to be intelligent, you have to move. And it's because as an entity in reality, you have to be able to test reality with your movement and test and know what's the difference between you and the rest of the environment. Okay, so let's talk about brains. I hope this animation is going to come through okay. But this is the brain. This is your neocortex. It's the squiggly part. And if you were to stretch it out, you can't really do this, but if you were to stretch it out, it would be about the size and shape of a dinner napkin. And this is a completely homogeneous structure. And there's this repeating unit throughout it. We call this a cortical column. And this was discovered in the 80s by Vernon Mountcastle. He sort of defined the structure that is repeated throughout the cortex. And we've also known that the cortex has these layers. We've known this for over 100 years. This is Cahal, and he drew these tons of pictures of these different layers of the neocortex. But the discovery of these columns and what they might mean for intelligence is a bit of a newer discovery. So now we have this idea of layers and columns, and this is, so we're trying to kind of put this together because columns contain these layers. These things work together, and layers contain lots and lots of neurons. There could be up to 100,000 pyramidal neurons inside each layer of cortex. So we're kind of getting smaller and smaller. So let's talk about this pyramidal neuron. This is sort of the atomic processing unit of HTM theory, or the theory of intelligence that I'm essentially driving at right here. And this is basically what Edward's going to build upon when he talks about anomaly detection. Just to give you some context, in the next talk that he talks about, this is like the core technology that he's going to build upon. Anyway, it's based on the idea of a pyramidal neuron having not only an inactive state and an active state like it would in any current ANN system, but also having a predictive state. And this is something that your brain's doing all the time. Your brain is like a prediction engine. It's constantly predicting what's going to happen next, right? All the time. And when something doesn't happen that you expect to happen, you're surprised and you're shocked because you had predicted certain things to happen that were represented by certain neurons, and those things didn't happen. I'm going to show you some examples of that in simulation later. But the important thing here, again, with the pyramidal neuron, aside from having these different states, is it needs different sort of integration zones. So a neuron doesn't just get stimulus in one way. A pyramidal neuron in the cortex can get stimulus in at least 3 different ways. It can get different types of dendrites that it has. Proximals, very close to the cell body, distal dendrites or basal dendrites that can get connections from far out. And then there's apical dendrites that typically get feedback. So these have to be considered as well in a model of intelligence, I believe. And we're completely missing this in current ANN systems. So since we're talking about the pyramidal neuron, and I said a layer inside of a column contains all of these pyramidal neurons, up to 100,000 of them, the idea that a neuron has these different integration zones then applies to the layer. So if you construct a layer out of all these pyramidal neurons and they're all oriented in the same way, which is true, you can talk about the layer itself as having these different sort of I/O channels. Layers are like little compute modules. They're made up of all of these different neurons, and you can pipe driver proximal input into it and distal input. The distal input provides context for a primary driving signal, which is the proximal input. And this is how it works in your cortex as well. These pyramidal neurons, the proximal input that's close to the cell body is what drives the cell to fire, but the distal input provides context and puts the cell into a predictive state. Now, there's lots of details that I have on this that I'll point you to some really good references at the end, but I'm not gonna go into detail about all of everything here. But I'm gonna show you some simulations. So, when I show you the simulations real soon, this is what a layer is going to look like for me. So it doesn't really look like a cube, but what this is a grid of a bunch of different. It's like a whole bunch of pyramidal neurons in a structure. Just a 3D grid basically, and the different colors are going to be different states of the neuron. So I'll explain that. But when you see this represents a layer like I've been talking about, which is one of these compute modules. Okay. So is everybody following me? Somebody wave your hand if everything's cool. Okay, I just want to make sure. Back to this. So I'm going to talk about sparse distributed representations for a minute. So you see the fiber optics cable. I hope that's sort of my visual, but I'm going to let me talk about this. This is a little bit easier face-to-face talk about. You mean? Okay. So imagine a neuron in your brain. This neuron has possibly tens of thousands of synapses across all of its dendrites that has grown out throughout the space of the brain. If you took all the synapses and sort of looped them together and wrapped them up in a bundle, it might look like a fiber optics cable, like if you stretched it along its dendrites. And indeed, if you were to be able to look at your spinal cord or your optic nerve, you would see axons, and it would look like a fiber optics cable. And 2%, essentially, in your brain, if you were to take a snapshot right now, 2% of your neurons are currently firing. That's very sparse. That's not very many neurons that are firing. But that's the way your brain represents things constantly. It's a very sparse activation of neurons. This always kind of puzzled neuroscientists. But we think this is a very important property that the brain takes advantage of to the extreme when it recognizes patterns that are sensory patterns in the input. So you can imagine one neuron as having sort of its perspective of the landscape of all the neurons it's connected to could be represented in this sort of bit array. And so now I'm going to go back and talk some capacity, and I'll give you some examples that will probably put this into perspective. Okay, so does everybody see my screen? It's a big grid. Yeah, okay. So this is an SDR, this big grid, and it's just, you can think of it as a binary array. It looks like it's 2D, but it's really not. It's just a one-dimensional array that's wrapping around. Let's see, do I have my, okay, so here we go. So it starts here and it goes down. There's 256 elements and only 5 of them are on. That's what this W is. I can make many more on. Now I've got 96 on, or 37% are on, but I'm going to go back to 5. If I have 5 bits on in this 256-bit space, these 5 bits can be arranged in this space 8.8 billion ways. So that's pretty high. And it's a little bit surprising. It's true that if you make it, the higher you make this, the amount of bits that you're using, the higher the capacity goes. But even at this, even with just 5 bits, 8.8 billion ways, that's a pretty high capacity. But we typically use SDRs that are in this range, like around 2,000 bits, and we'll turn 40 of them on, to keep it around 2% capacity. And so now the capacity is so astronomically large, it's as big as there are atoms in the known universe. So to drive home the point here, in this space, like this grid that you're looking at right here, it has the capacity to essentially represent anything forever. And that this is the representational space that your brain is constantly taking advantage of. So there's that. The other thing is with SDRs, see if I can make this a little bigger. There we go. So here I've got 2 random SDRs. I've got one on the left and then one in the middle. And I'm just randomly created these 2 SDRs. And then on the right, I'm comparing them. And what I'm showing right now is the overlap. These are all the bits that are shared between these 2 representations. Okay, if I can also show the union, this would be all of the bits from both of them. So what you can see here is the value of this overlap is this overlap shows you all the semantically similar bits between these 2 things. If you can imagine every bit having some semantic meaning or having some meaning, then you can compare 2 things and tell in what ways they might be similar. The union also allows you to stack things together and compare other things to it to see if it is a member of that set. So these comparison operations, and I have some other examples of this that I don't have time to get into. These comparison operations of SDRs are really really important. Okay, so that's like the communications medium of the brain is this idea of sparse distributed representations, and they always represent neurons and whether they are firing or not, typically, pretty much. So how do we get data into the system? This is the hard part, okay? And our brains are the things that encode reality into this binary SDR space are your senses, your somatic senses, your skin, your ears, your eyes. These are your encoders. These are the things that create that bit, that fiber optics cable that pipes into your brain. Now, we're not in the business right now of trying to recreate senses. We're trying to study the cortex. So we've created some encoders, but they're not biologically accurate at all. We just needed to create encoders that work, that encoded semantic information in the way we theorized that the brain needed it. And so that's what we're doing. So what I'm trying to show you right now is a date encoder. This is not a sense that anyone has. This would be like if you had a watch attached to your brain at all times, and you could constantly pull up exactly, not only like the second of the hour and the second and the day, but you could tell like whether it was afternoon or morning without looking outside, that sort of thing. So here's how it works. This is today. This is Thursday. It's 4:22 a.m. here in California. But if I move forward a week, this is what I'm doing. I'm jumping forward a week from the 17th to the 24th. You can see there's a bit over here of the season that's moving. As I continue to move through the year, the season changes. If I move through the day of the week representation changes. So each one of these grids here is a different SDR representing different semantic information about a date, a timestamp. And what we can do is put them all together. And we can take this encoding and this encoding and this one, and we can put them all together in one encoding here. So as I move through time, the entire encoding is going to encode all of these 4 different dimensions of time semantics. So that's an example of how an encoder might work. Let me show you a little bit more of an interactive, or maybe not. Okay, apparently this one doesn't work. Oh, I got an idea. Hold on. I think this is going to work if I do it in Chrome. Oh. Okay, so my that demo is broken. I'm gonna have to fix that. But here's another example of an encoder. Turn this debugger off. This is a scalar encoder. This is super simple. This is a value from like 0 to 100. I can change the min and max. I can change how many bits I want to represent the value. I can change how thick I want the representation to be. Okay, this allows me to make encoders that will encode, for example, the value 57, to 88, and have a bunch of overlapping bits so that these values are similar. Another way you could do the exact same thing is to not have a continuous bucket, but distribute the bucket through the space. The point being, there is a ton of different ways to encode information. You could take the number 3 and encode it thousands of different ways into this space. That's however you use to encode the space is your it's an engineering decision at this point. Okay. How much time when am I supposed to stop, Lee? Maybe you should let me know when I have a few minutes left. So I'm going to get on to spatial pooling. This is
Sorry, yeah, some time. You may proceed.
How much time? Sorry.
Roughly around 15 minutes.
Okay. Okay. Spatial pooling. So this is where it gets a little bit deep here. So the idea behind spatial pooling is within a layer of all of these neurons are grouped. They're grouped in mini columns, as we call them. But really, the real point is they have to be grouped. And within this group, each group shares a receptive field to the input space. So each of these groupings has the same view of the input space, and they're all sort of randomly initialized. And the whole point of this is to take that input and transform it into another space, so where we have control over the sparsity of the representation, and the semantics have to also be retained. So I have another demo, and I'm going to hope that it works too. Input space, overlap, connected synapses. It's one of these. Okay, cool. Okay, so do you guys remember? So I showed you that layer in software, right? That big three-dimensional cube. So imagine on the right here, we're looking down on that cube from above. Okay, so these are columns looking downward from above. I'm going to click on a column to sort of set it. And what it's showing over here is its potential pool of connections that it could connect to. Those are the orange squares. These are all the possible spaces, or all the possible cells in the input space that it might create a connection to. The interesting thing is every single column has a different set of potential pools. None of them are going to have a representation of the space like any other column. They all have a different representation of the space. In addition to this, they all have these permanence values. So it's not just a pool of potential connections. Every one of those has a value associated with it. If that value reaches a threshold, and this is a scalar value, basically from 0 to 1, if that value reaches a threshold, then you would say the connection is on. Everything okay? I thought I heard something. Okay. So if this value, and I think, I want to try and show this chart over here, but it's not showing up. So all of these blue dots here are connections from this one mini column to this whole input space, to a cell in the input space where the permanence value for that synapse is above a threshold. So we're going to call all of these connected synapses. All of the red ones are potentially connected synapses. They could connect at some point, okay? And every single one of these columns, these spatial pooler mini columns, is initially created with a different sort of random spread of permanences and connections around a certain threshold. So they're all primed to learn right away. Like all of these connections are really close to the threshold, so that a bunch of them will start learning and forgetting right away, sort of to prime it to learn. So that's sort of how we map a column in the spatial pooler to an input space that you might encode data. So now I'm going to show you how the spatial pooler learns. So this is sort of the same type of view here, okay? But what's different here is I'm actually showing an input here. I'm actually showing what, you know, some typical data might look like. This might be the value 47, and this is on a Tuesday at 7 a.m. I don't know. But there's some semantics in this data. So given that we've got a spatial pooler and all of its mini columns have been initialized, like I sort of just described, we can go look at each one of these columns, each one, and say, based on all of my connections, how many overlap the current input? That's what I'm looking at here. These green connections currently are overlapping the current input. All of the gray are connections that don't overlap the current input. So I'm looking at this first column, and there are not enough connections overlapping the input for it to become active. Okay, so now let me look at one of these active mini columns. This one apparently has 46 overlapping connections with the bits in the input space. That's why it's active. So basically what we're going to do is we're going to stack rank every one of these mini columns based on its overlap score, its connections overlap score with the current input. And these are the columns that are going to essentially win, because they're competing to see which columns are going to represent this particular input. These green columns on the right are what the spatial pooler has chosen to represent this spatial input that we're seeing on the left. Over time, now that we have these columns that have learned or have been selected to be active, now when they're selective, we're going to increment the permanence values for the connections where the overlap occurred. This is Hebbian learning, basic Hebbian learning. And we're going to decrement the permanence values of all the connections that fell outside of that input. So what this is going to do is it's going to have columns that learn over time to select certain features, certain spatial features out of the input, and sort of grow an affinity to certain spatial features in the input. So this column might learn over time to represent part of the space in this area, part of the space in this area, you can't tell what it's going to represent. It's going to choose what it represents over time. Okay, that's spatial pooling. Let me go. I think I got more slides now. Okay, so we've been talking about just proximal input. This is all proximal. So all of the groupings and the spatial pooling, but there's something else going on here within these mini columns. I keep talking about mini columns and columns, but I'm not explaining why those even exist. Well, you can have any number of cells within a mini column, and these cells make connections to each other. Within a layer, they make distal connections to each other. If you remember, distal means these connections that are lateral. They're contextual inputs. The spatial pooler, the spatial input, the sensory input is proximal. It's driving the cell to fire. But the distal input that it's getting from itself gives it context. So you might think about it this way. If your context is your past, then you have a temporal system. And that's basically what we're doing, is we're telling the cells to connect to themselves. And they're basically connecting to a previous state of itself. If you can think of the collection or population of cells in a layer as having a state, when it learns a new sequence, it basically connects to a previous state of itself. That's what temporal memory really is doing. It's identifying this context of input with distal segments. And so now it's time to do yet another demo here. Okay, this is the coolest one I have. And it has sound. I don't know if the sound's going to come through. Let me. Okay. Is this going to work? I hope you can hear that. Shout if you can hear that. Okay, great. Thanks. Okay. Hopefully it's not too loud. All right. So I'm running an HTM. This is NuPic. This is the one that Numenta created. And what I'm doing here, and it's learning this little sequence of notes. I'm going to pause it. And the sequence, okay, here it's learning A, C sharp, E, A, and I'll keep it going. There we go. I'll just turn it down. Over here is the encoding on the left. This green thing, you can see the notes sequentially being encoded in different blocks. I just hard-coded those. So these are just different ways to represent these notes. They're completely different. There's no overlap at all. Over on the right here, this is a layer. So this is sort of a layer looking down on it from the top or up out from the bottom. And I'm going to spread it way out so you can see these yellow columns sort of appearing and disappearing in the layer. I'm going to pause it now. So this is a mini column in the layer. We should turn this off. But as you can see, so for this input, these are the mini columns that is chosen to select, and you can see them a little bit better here. Sorry, it's a little. But this represents C sharp. If that makes sense, right? Right now we got C sharp as an input. This set of active columns represents the spatial pattern for C sharp. The next one is going to be E. So I step forward. Here's the E input. This is a spatial pattern for E. Okay, this is a little deep. I'm checking in with it. Raise your hand if anybody's following along with me at all. Okay, I got a few hands. Okay, that's good enough. Okay, so I'm going to spread this back out because I want to show you it's really important how cells activate within a mini column. So there's two ways a cell will activate within a mini column. Well, let me show you something first. This loop. This A, C sharp, E, A loop is played over and over and over, but at the end of the sequence, I'm manually resetting. I'm basically telling the system that's the end of the sequence. If I don't do that, in a temporal system, and you're looping, how do you know when to stop? How do you know when the sequence is over? So you just have to sort of tell it to stop. So when it sees this first A, it always sees it sort of out of context. It never sees anything coming before it. So I'm just going to caveat with that. So I'm going to show you what the active cells are. Okay, so now we're at C sharp, okay? These yellow mini columns are the spatial representation for C sharp. What comes next is the spatial representation for E, then A, then another A. Okay, but now I'm going to show you the predicted cells. Okay, so I told you there were two ways that a cell in one of these columns could become predictive. I'm going to show you one way now. Let's say we just get this input. We just got this input for C#. The first thing we do is look and see what active columns came up, and were any of those cells in that active column predictive in the last time step. So we're asking ourselves, is this input expected or not? All of these predictive cells in these mini columns tell me that this was predicted. So the system says, oh, then these cells are active then. Since it was predictive in the last time step, they were all correct, it's going to make them active cells. Okay. The other reason why a cell might become predictive, let me scoot forward to A. Okay, I told you the first time we see A, let me turn the active cells off first. We see it out of context. It's just A. Nothing came before it. So what happens is it gets to this point and it's looking for predictive cells. Let me turn the predictive cells on. There's no predictive cells because nothing has ever come before A before. So what it does when there are no predictive cells in an active mini column that has been activated, it will activate all the cells in the mini column. So what this does is it basically says that there's a potential fork in this sequence. This fork, I don't know where it's going, but something stopped here, and this could go in many different directions. This is called bursting. This actually happens in your brain when you're expecting one thing to happen, and something very different happens. A bunch of neurons in your brain fire to go in a bunch of different possible predictive directions because you don't know. You're confused. This is sort of an idea of confusion. So those are the two ways something could fire. It can become active if there was nothing predictive, and it's one of those cells is going to burst. And then over time, as it sees a pattern over and over, it will select one of these cells to represent that pattern transition over time. But for right now, it's just bursting. And the other one, like I said, is if we see predictive cells from the last time step in the current space, then we're going to make those active. Okay, I got one more neat thing I'm going to do here. Let me play. I've been playing this for a while, and let me ask you a question. What's going to happen? I'm going to stop this at C#. So I can't see you guys, but maybe you can participate here and shout out. If what I'm looking at here are the active cells that represent what note? Can anyone tell me? I'm hearing C#, right? So we're looking at C#. This is a spatial input for C#. This is the spatial pooler's representation for C#. Predicted, these are the cells that we're predicting are going to come next. What cells are we predicting? These should be the cells that correspond to what note? E, because that's what we've seen in the past, right? We've seen A, C#, E a bunch of times in the past because I just let it play. So we're obviously expecting E to be next. What's going to happen if I don't play E? What's going to happen if I play something we've never seen before? Anyone? I can't really hear very well, so I'm just going to keep going forward. I'm going to step one step forward, and all of these predictive cells are not going to fire, right? They're not going to fall within active columns because we're not activating E. We're activating F#. And F# we've never seen before. So all of these columns that become active burst because we've never seen A, C#, F#. We've only seen A, C#, E. And then there's this one column over here that just randomly shares some semantics with E, apparently. So it fired. But that doesn't matter. I mean, that sort of stuff gets washed out over time. I mean, I didn't mention it, but I could add noise. I could probably add 50% noise to this, and it would still work. The noise tolerance to this system is really, really good. Okay, so I'm gonna start playing this now. This new sequence, A, C#, F#, A, and it's gonna learn it over time. And after a while, it's gonna stop bursting. Looks like it stopped bursting. So now we're at C# again, but we're not bursting anymore. Looks like we have a prediction And the prediction, or excuse me, so let's look at the cells that we're predicting could be next, right? So here they are. These are the predicted cells. Now I'm sitting at C#, but if you're an astute observer, you might notice that these are twice as many predictive cells that we had the last time I inspected them at C#. Why? We're predicting both E and F#. So we're seeing a combination or a union of the SDRs for F# and E following C#. What we have here is a sequence memory system that is, what do you call it? A high order memory system, a high order sequence memory system. So that's what I think is really impressive about this, and it's in your brain. It's it's amazing. Okay, so that's my brain demo. I need to probably wrap up here, don't I? So you're probably thinking, you know, I explained this whole idea of a layer as being a compute module, and what I just described to you was the distal input coming back into itself, right? I talked first about a layer being, it can get its distal input from anywhere, but in this model, it's getting it from itself. That's what makes it a temporal model. But you might imagine this distal input coming from somewhere else, other parts of the brain, and representing other things. So a big part of our sensory motor research right now is trying to figure out how location can be represented and in the brain using grid cells and sent in as a location signal, so that when we use sensory input and tie it to a location in space, we can use that for object recognition. So that's sort of our current research direction. And I've got lots of information about that, and I don't think I have time to actually show you a little demo of it. But it's what we've been focusing on for the past year and a half at least, and it's really cool stuff. We have papers about it. But let me give you some resources, and then I'll take some questions. First of all of our stuff is open source. It's called the Numenta HTM implementation. The official one is called NuPIC, or the Numenta Platform for Intelligent Computing. All of our research code is also open source. And all of our research papers are completely accessible and free. That includes this one, Why Neurons Have Thousands of Synapses, which completely explains that whole phenomenon of, you know, apical versus distal versus proximal inputs, and why dendritic spikes are so important to our model, which I didn't touch upon very much. And the last thing I want to show you is I have this YouTube channel. Let me ask you guys. Raise your hand if you've seen any of my YouTube videos about HTM. Okay, a few people. Okay, that's good. That's good to know. If you're interested in this stuff, I go like ad nauseum into this on YouTube. I've got like 14 different YouTube videos just about HTM theory, about how important spatial or sparse distributed representations are, how bit arrays work, you know, from the bare basics all the way up to sequence memory and dendritic spikes. And even the last one I did was about grid cells and about the properties of grid cells that we know are going to be important for how the brain represents location. Okay, last slide, I'll take questions. This is just an informational slide. All this stuff is at numenta.org or numenta.com. You can see me on Twitter or at GitHub at Rio Light, and same thing with Numenta. And I think I'm in a position where I can take questions. If there aren't questions, I think someone should probably come up to the computer so I can hear you. Or you can type them into chat.
Hi, any questions?
Okay, hi Matt, thanks for your presentation. I think the whole spatial cooling that you just described kind of reminds me of CNN, whereas the temporal model somehow looks a bit like RMN. So do you mind giving a brief explanation of how HTM differs with, you know, the other deep learning models?
So the spatial pooler is not doing anything temporal at all, as far as taking an input space and transforming it into another space. It's doing some type of transformation. It's taking all the bits here and turning them into another set of active bits here that we have control over how that's represented, basically how dense we want that semantics to be represented here. And then it learns, it does Hebbian learning over time. So I don't know how close that is to, you said CNNs, right?
Yeah.
I don't know what concepts of CNNs that maps onto.
I mean, as far as I'm aware of, CNN kind of like you have multiple layers, and then each node, or rather each node in a big layer, right, it kind of maps into a whole space, like some other nodes in the previous layers. So like you have that kind of spatial view. Correct me if I'm wrong. Like each neuron has that kind of spatial view of the previous layers, and then you map it into another number, and then you have a set of matrix operations. So I mean, the model at a first glance looks a bit like that. Maybe I haven't fully understand how HTM works, but maybe like just to give a brief overview, what is the main difference between HTM and other?
The main difference, let me tell you that. HTM is completely temporal. It depends on temporal streams of information. HTM will not do image classification like current deep learning networks do. That is all massively spatial classification, and that's not the way your brain does image classification either. If you were going to try and do that type of classification with HTM, you would want a sensor that could move through a space. So that way you could make the input temporal. You have to somehow make the input temporal. You have to scan the image or something. And if you think about it, that's how your brain constantly perceives the world. The reason why HTM works like that is because we're trying to figure out how the brain does it. The brain constantly processes streams of temporal information, and that's why HTM does too. And there's in CNNs, I know you can have lots and lots of hidden layers, right? And hierarchy and that stuff. So the H in HTM stands for hierarchy, right? But we're not using it at all in any systems currently today. We think you have to have hierarchy eventually, but you also, by definition, if you're going to build a hierarchy, you must understand how the repeated node in the hierarchy works. You can't put the hierarchy together without understanding that node. And we believe that cortical column is a key component of that node. That is a node in the hierarchy, how it shares information at the level it's on and how it passes information up and down. So we're focusing entirely on that one node of the hierarchy, and knowing that, you know, we'll put the hierarchy together once we understand the node better. I know I got a little bit off topic, but the main thing is temporal versus spatial. Most ANN systems today are awful at temporal anomaly detection or classification or temporal streams. LSTM is one of the better ones, but HTM can still beat that at anomaly detection. I think Edward hopefully will talk about this, but we do have sort of a benchmark for anomaly detection called the Numenta anomaly benchmark. So we do compare this to other deep learning systems, or most of them aren't. Most of them are just other methods of doing streaming analytics, because that's not something that deep learning is great at right now. But anyway, sorry, I digress.
So you mentioned that HTM is completely temporal in nature. Does it mean that it suffers from the same constraint as R and N, where the computational time is directly related to the sequence length?
No. No. Now, so the way we do HTM right now is we never end any sequences. If we're doing anomaly detection, so that doesn't seem to affect it. There is a maximum capacity that you will eventually reach. But then at that point, you just start forgetting old sequences. But it doesn't matter how long the sequences are now. I mean, if you think about it, you can jump into a sequence from any point. You don't have to go back and retrieve any of the past information. You can just jump in after you see a couple of them. It's like you're picking up sort of a web and you can see all these potential sequences back in the history. You don't have to follow any of them back unless you're trying to identify them. But
Any other questions?
thank you.
Right. Okay. Thank you, Matt.